Okay, so I want to start this week by talking a little more about the similarity of two matrices, and then I also want to talk about the trace of a matrix. And really, this is just kind of a prerequisite lecture for the main topic of diagonalization. So first, let's recall what it means for two matrices to be similar. So let's let A and B, these are going to be n by n matrices. And then we said A, and I'm going to adopt the notation that this squiggle here means similar. So when I write A squiggle B, what this means is that A is similar to B, i.e., there exists an invertible matrix P such that you can write A as the product of P inverse times B times P, right? And we now understand what similar matrices are and how to find them, or how to find the invertible matrix P for two similar matrices. What I want to do now is discuss the behavior of similarity as a relation, right? So what does that mean? What's a relation? And we'll say a relation on a set S. Okay, so let's say S is, it doesn't have to be finite, but for this context, let's just say S is a finite set with elements x1, x2, up through x alpha, say. Then a relation on a set is just that. It relates to elements, right? So a relation is, and I'll say a quote unquote partial ordering of all elements of S. So the most used or familiar examples would be equality, right? That's a relation for a given set. Say the integers, it relates when two integers are the same, right? Or maybe if you were taking like absolute value of x and negative x or something like this, right? So we have equality, and then you have things like less than or equal, greater than equal, etc. Right? So this is the kind of informal introduction of a relation. And so what we want to do is we're going to realize similarity as a relation. And more than just a relation, we're going to prove that it's an equivalence relation. So first, let's define an equivalence relation. A relation, squiggle, is an equivalence relation if, so let's say it's an equivalence relation on a set S with elements like A, B, C, etc. Maybe finite, maybe infinite, whatever. So a relation is an equivalence relation if we have the following conditions. For every element A, B, C in S, we have the following properties. We have that A is related to A. This is called the reflexive property. We have that A related to B implies B is related to A. This is symmetry. And then we also require for a relation to be an equivalence relation, we also require that, let's say for A equivalent to B and B equivalent to C, this implies that A is equivalent to C. And this is called the transitive property. An example of something, you may say, well, those are pretty common properties or things that could easily be satisfied. Well, for an example, let's look at strict inequality, right? So less than or equal to, or greater than or equal to. These aren't reflexive, right? Because A less than A is not true, right? And certainly symmetry does not hold. If you were to say A is greater than B, well, for this to be an equivalence relation, that would have to imply that B is greater than A, which is not true, right? It's contradiction. So there's an example of something that's not an equivalence relation. And what we're going to prove, here's the theorem, similarity is an equivalence relation. And let's prove this. The proof of this is within our abilities or our scope of understanding. So what do we need to do? We need to show three things. We need to show that A is similar to itself. We need to show that if A is similar to B, then B is similar to A. Then we also need to show that if A is similar to B, B is similar to C, then A is similar to C. So let's start with the first one. What does A symmetric mean? Or, right, if A is similar to A, we need to find an invertible matrix P such that A equals P inverse A P, right? This is what it would mean for A to be similar to A. Well, just take P to be the identity matrix, right? Which would be 1, 1, 1, 1, zeros everywhere else. That's clearly invertible. If you take P as the identity, it's its own inverse, right? And so we're good there. So we found that similarity is a reflexive relation. Now, what we want to do is assume for proving symmetry, right? We want to show that if A is similar to B, then we need to somehow conclude that B is similar to A. Well, let's start with what we know. We know A is similar to B. This means there exists P, blah, 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 such that A equals P inverse B, P. And now what do we need, right? To show that B is similar to A, we need to swap the roles of A and B in this equality here, right? Well, how can we do that? If we start with A equals P inverse B, P, let's multiply on the left both sides of this equality by P, right? So then we would have PA equals P inverse BP, which is BP. Well, then let's multiply on the right by P inverse. So we would have PA P inverse equals BP P inverse, which is just B. And so since equality is a transitive or is an equivalence relation, equality is transitive, right? A equal to B, B equal to C implies, right? A equal to B, B equal to C. Equality is transitive. And so we've proven then this shows that B is similar to A. Cool. Now what about transitive? We want to assume that A is similar to B and B is similar to C. What does this mean? Well, this means there exists invertible matrices P and Q such that A is equal to P inverse BP and B is equal to Q inverse CQ. Now, what do we need to show, right? The objective is to show that A is similar to C. So we want to show that there exists a matrix smiley face, can't think of anything else, such that A is equal to smiley face inverse C smiley face, right? So what we need to do is we need to construct this matrix smiley face, if it exists. Well, what do we know? We always start with what we know. A is P inverse BP, since A is similar to B, but B is similar to C. So we could replace B by P inverse Q inverse C Q P. And then by the associativity of matrix multiplication, this turns into P inverse Q inverse times C times QP, right? And now if you'll remember, a property of inverse is if you have the product of the inverses, when you go to the inverse of the product, you have to flip the order, right? So this is equal to QP, right? We flip the order, QP inverse C QP. And then, there's a subtle statement here that needs to be made, and that's to recall that AB invertible implies the product is invertible, right? So that's a subtlety here. Well, then we set smiley face equal to QP, which implies that A is similar to C. Cool, QED. So while this is on my mind, I remember when I was an undergrad, I had trouble with understanding why the inverse flips, right? Because normally for an exponent, for exponent laws that we learned back in like kindergarten or whatever, it's if you have x to the a times x to the b, well, that's x, or let's say y to the a, right? Well, then that's just xy to the a, right? It doesn't flip or anything like this. So why does it flip? Well, with matrix multiplication, we can think about it as the following analogy. Well, one, we know matrix multiplication in general is not commutative, so that matters. But let's consider the following little example. Let's say this is me. Draw my super cool hat here. And I'm trying to walk through a door. And let's say P represents me opening the door, and Q represents me walking through the door. Now, what would let's think about this multiplication as a composition, right? Because that's really what it is. Let's say we were to do QP, right? Like we have here. Well, then that means you multiply, or you do P first, right? If you're thinking about this as composition. So P, so after I P here, then I open the door. So, new schematic. Now the door is open. And then after Q, I walk through the door. There's me on the other side. Now let's say we want to do this in reverse, right? If we want to do this in reverse, and let's say, well, what if PQ, or QP rather, what would happen if QP inverse was just Q inverse P inverse, right? If I wanted to do this action in reverse, well, then we have a new scenario, right? I'm standing on the other side of the door with it closed, and I want to walk back through the door. Well, if inverse doesn't flip, then I do Q first, and I try to walk into a door that's not open, right? And so because of this, this is just kind of a little helpful maybe mnemonic device here that will help you remember. When you take the inverse or the product of the inverse, when you switch it to the inverse of the product, you have to also switch the order of the matrix multiplication. Okay, so now another prerequisite definition we need here before we can talk about the diagonalizability of a matrix is we need the notion of trace here. So let's say A is a n-dimensional or n by n square matrix, right? Say something like this. And we know along the diagonal, we have like A, 2, 2, et cetera, et cetera. Then the trace of A is, and it's defined to be the sum of the diagonal entries. So the trace of A would be A11 plus A22 plus blah, 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 up to ANN, or written compactly, we use summation notation. Let's say this is the sum, I goes from 1 to n of A, I, right? So it's a very, very simple description and pretty easy to understand, right? You just take the diagonal of a square matrix, sum it up. Let's look at some properties of the trace, right? We have that the trace of the sum of two matrices is the same as, first you take the trace of A and then plus the trace of B. We have that if you take the trace of a matrix scaled by some real number K, well, then that's the same as scaling the trace, right? So this is for K in R. And then lastly, we have that the trace is invariant under order of matrix multiplication. So even though AB may not be equal to BA, because matrix multiplication is not commutative in general, we still have that the trace is the same. And I would really, so here's like a task or a challenge. Prove these. Right, and here's my hint. My hint is to explicitly write out a matrix A and a matrix B. Maybe start with an example, right? See, like, say A is some 3 by 3 matrix, like 1, 2, 3, 4, 5, 6, 7, 8, 9. And then B is a matrix of all ones or something, right? See if you can verify all of these properties for an explicit example, and then see if you can prove them in general. So that's kind of a challenge or a homework problem that goes unassigned. The last thing I want to do is talk about how the trace relates to similar matrices. So here's a theorem. Let's let A and B, these are going to be n by n matrices. And let's also assume that A is similar to B, right? Then we have all sorts of kind of conclusions from just knowing that A is similar to B. We have that the determinant of similar matrices is the same. We have that the rank of similar matrices, whoops, is the same. We also have that the trace of similar matrices is the same. But we can say even more. We can say that the coordinate vectors for similar matrices are the same, which a priori, that's pretty shocking, or you may not believe it, right? Like, well, yeah, they're similar, but there's no reason that with respect to some arbitrary basis, there's no reason that coordinate vectors need to be the same, right? The entries of similar matrices can be arbitrarily different. But we do, in fact, have that the coordinate vectors, with respect to some fixed basis, these are indeed the same. And then we also have that and I think we know this already, that A and B have the same eigenvalues. Okay. So, and if you really want to challenge, so here's challenge is equal. I would challenge you to prove all implications from this theorem. So start with similar matrices. So, like to give you kind of a hint here, you would start with A similar to B. Well, that implies there exists an invertible matrix P, blah, 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 such that A equals P inverse BP. And then to show that the determinant of A is equal to the determinant of B, what would you need to do, right? Well, you would need to take the determinant of both sides of this equality, right? If A is the same as this product, well, that implies the determinant is the same. Right? And we also know that the determinant of the product is the product of the determinants. So on the right-hand side here, this would be the determinant of P inverse times the determinant of B times the determinant of P. And now what could you do from there, right? So there's my hint for, this would be for the proof of 1, right? So you can start there. And I would challenge you, I would say if you can prove this or get yourself on the right path, that would really increase your understanding of what it means for a matrix to be similar, right? So I think that's the end of my prerequisite discussion and material to get to the topic of being able to diagonalize a matrix and things like this. So in the next video, we will introduce the notion of a diagonal matrix and see what it means, or when an arbitrary matrix can be converted into a diagonal matrix.